Welcome to the third module, lecture 5 of the course called Game Theory and Economics. Before we start today's lecture, let me take you through what we have been discussing in the previous lectures. So, we have been discussing the various applications of Nash equilibrium in game theory, and the model that we have been discussing so far is the Bertrand model of oligopoly. So, this is a model about markets. Here there are some firms who are trying to sell their goods to the customers, and what they are aiming at is to maximize their profits. The important thing about Bertrand competition is that the firms, they sell the similar goods. You cannot distinguish between the product of firm 1 and firm 2, and while selling their goods, they decide the price of the good. So, it is the price of my product on which I have control. How much what will be the level of output is not something which is directly determined by me. Given the price that I quote for my product, there will be some demand for that for my products in the market, and whatever be the demand for my products, I have to meet that demand. So, the level of production in the market is something which is not directly determined by me, it is determined by the demand side of the market. I only decide what will be the price of my product. So, this is the setting, and so far we have seen that in this market, if we simplify the story a little bit and suppose there are only two firms, we are going to generalize this model later on. So, for the time being, suppose there are only two firms, firm 1 and firm 2, and their unit cost of production is the same, small c, and suppose the demand that they face is a very simple kind of demand function given by linear demand function. Then we have seen that in this setting we can find out the Nash equilibrium, and we were in the process of finding that Nash equilibrium. And how we tried to find that Nash equilibrium is to construct the best response functions. So, we have basically so far constructed the best response functions of firm 1 and firm 2. We have seen that for firm 1, the best response function is given by Q1, which is a function of Q2, and this is given by a set of 3 ranges. So, this is the best response function of Q firm I as a function of, it is the price that they are determining. So, the price that firm I decides is given by Pi. It is a function of Pj, the price that is determined by the other firm, and we have seen in the previous lecture that there can be 3 different values or range of values of Pj which we have to consider separately, and for each case the best response of firm I will be different and given by this set of values. Now, given this, what we can do is to plot this best response function for firm 1 as well as firm 2 and look at what is the equilibrium. So, suppose this is C and suppose this is PM what we know is that if P2 is less than C, then P1 will have to be greater than P2. So, here is this point CC and suppose this is the point PM and this is the 45-degree line. If P2 is less than C, that is we are talking about this range. If P2 is less than C, firm 1's best response is to charge a price which is strictly greater than P2. So, all these points will be covered by the best response functions. But not these points on the 45-degree line. If price of firm 2 is exactly C, then of course this point is going to be covered. So, this I am writing as a dot, a black dot, dark dot, and these points to the right of this dot are also covered under the B1, that is best response function of firm 1. If firm 2's price is greater than C and it can go all the way up to PM. At the value PM, the firm's monopoly profit is being earned. So, at PM the profit of each firm is maximized. So, if firm 2 is charging any price between C, not including C, more than C, and it can charge a price equal to PM, the best response for firm 2 will be charge a price which is just a little less than P2. But the point is that there is no one best response function here. So, whatever be the price of firm 2, I can never define P1 which is closest enough to P2 because P1 is a continuous variable. No matter what closest P1 one proposes, I can propose some other P1 which is even much closer than that P1 to P2, which means here there is no best response function up till PM. If firm 2's price is greater than PM, then firm 1's best response exists, it is given by PM. So, I have this vertical line here, and here I have this, so this is PM. Here I have this circle which is an empty circle, which means that this point PM point is not on the best response function of firm 1. So, this is how B1 P2 looks like. And similarly, I can define or I can plot B2 P1 suppose C is here, PM is here, C is here, PM is here. Now, here what will happen is that if P1 is any value less than C, if P1, this is the point CC, if P1 is any value less than C, can go all the way up to the 0, firm 2 will charge a price higher than that price. So, if this is the 45-degree line, all these points in this shaded region will come under the best response function of firm 2. At C, if firm 1 is charging the price C, not only those points which are on the vertical line will be covered, but CC point will also be covered. So, I have a black dot from C to PM. So, this is the point PM. From C to PM, there does not exist any best response for firm 2. The reason is as before, and at PM also there does not exist any best response function. So, I have a empty dot here. If firm 2's price is more than that, sorry, firm 1's price is more than PM, then firm 2 will go on charging the price PM. So, I have this horizontal line here. So, this is how these two firms' best response functions look like. And as we have just discussed before, how to find out the Nash equilibrium? Nash equilibrium is situated at the intersection point of these two sets of functions, and so we just examining these two and superimposing one on the other, I can figure out that this is CC, this is PM. That if I superimpose one on the other, I have this sort of a diagram. At PM I have a empty circle and I have these two horizontal vertical lines. So, this is how superimposition of two best response functions B1 and B2 will look like, and we see that there is only one point at which these two sets of curves are intersecting, are having some intersection, and that point is given by CC. So, CC is the Nash equilibrium. So, this is the equilibrium in Bertrand model, that there are two firms, they will in the equilibrium charge a price which price is just equal to their unit cost of production, which means that the price in the market is C, which means Q is what? Q is alpha minus C, because price is C, and which means that individual output level is going to be half of this alpha minus C divided by 2, and mind you, profit is going to be 0 here, because there is no difference between the price and the cost. Cost is just eating up all the price that the firm earns from the market. So, there is no profit, the firms are producing some output, and this is happening irrespective of the number of firms. If you remember in the Cournot model, this situation happened only if the number of firms became infinite, Here, even if there are two firms, the competition ensures that there is no profit earned by any firm. They are earning their normal profit. So, this is the story then in Bertrand equilibrium. It is much more different from the Cournot model that we have studied before. Now, this is a systematic exposition of the equilibrium, that we have this equilibrium at CC, but we could have used a more direct argument to say that this is the equilibrium, and this is the unique equilibrium, mind you, because there is no other point at which the best response functions are intersecting with each other. Why this is the unique equilibrium? We can show that in some steps. First, we have to logically argue why CC is the equilibrium. This is Nash equilibrium because of the reason that if the other firm is charging C, can I do better by not charging C? The answer is no, because when I am charging C, I am getting zero profit. The market is getting divided, and though I am getting half of the demand in the market, since the profit margin is 0, so my total profit is also 0. If I charge a price little less than C, the price that the other firm is charging, I get the entire market, that is true, but then my profit will turn to be negative, because then the profit margin is negative. If I charge a price higher than C, then obviously no customer is going to come to me, because my rival is charging a lesser price. So, in that case my profit remains 0, which means this is a Nash equilibrium. However, this is not a strict Nash equilibrium. Is there any other pair P1, P2 which is a Nash equilibrium? So, we have to show that CC is unique, that no other pair exists which is a Nash equilibrium. The reason is the following: suppose this other pair is such that the prices are different and both the prices are higher than C. If both the prices are higher than C, then there is profitable deviation for at least one player. The firm that is charging the lower price, it is earning profit because there is profit margin, but it can earn better if it raises its price just a little bit. It can earn higher profit because it still retains the market, because the other firm is charging a higher price. So, by charging a little bit more price, I still retain the market, provided of course that this P1 and P2 that I am considering are less than PM. And even if they are greater than PM, then any firm can earn higher profit by charging PM rather than their prices P1 and P2. So, if P1 and P2 are different and both of them are higher than C, then that cannot be a Nash equilibrium, that we have just argued. If they are equal but higher than C, can that be a Nash equilibrium? The answer is no, because in this case, when the prices are equal, the market is getting divided equally. So, any firm can just lower its price a little bit and can capture the entire market, and if it can capture the market, then it is getting higher profit compared to the case where the profit is getting divided. So, no pair of equal prices where the level of prices is greater than C is a Nash equilibrium. And thirdly, if the prices are less than C, then can that be a Nash equilibrium? If the prices are less, then suppose the prices are equal. If the prices are equal, then the firms are getting negative profit So, each of them will do better by charging higher price. So, that is not a Nash equilibrium. If they are unequal, again the firm which is having a lesser price, lower price, can do better by charging a price at least equal to C, then it is getting 0 profit. So, we are basically ruling out all these possibilities. Another possibility we have not considered so far is that one of the prices is C and suppose the other price is greater than C. But that also is not a Nash equilibrium, because the firm which is charging the price C can do better by charging a price just a little higher than C. So, in that case it will earn some positive profit. By charging C, it is getting 0. So, this is more or less the demonstration. We did not have to depend on construction of this best response functions to argue that CC is the Nash equilibrium in this case. Next, what we are going to do is to take some exercises and try to solve them. Consider Bertrand's oligopoly game when there are n firms with n greater than or equal to 3. Show that the set of Nash equilibria is the set of profiles P1, P2 Pn of prices for which Pi is greater than or equal to C for all I, and at least 2 prices are equal to C. So, here we have a general case, n firms are there, and what we need to show is that P1, P2, Pn is a Nash equilibrium if all the Pi's are either equal to C or more than C for all I, and at least 2 prices are equal to C. First, let us show that such a profile is a Nash equilibrium, and then we shall show that no other profile of different characteristics can be a Nash equilibrium. Now, if 2 prices are equal to C, at least 2, and other prices can be more than C, then notice that if my price is equal to C, I am charging the lowest price, then I am earning 0 profit. The firms which are charging more than C, they are also earning 0 profit. So, in this case nobody is earning any positive profit. Question is, can someone do better and earn some positive profit? The firms which are charging C, and there are 2 firms, at least 2 firms, if they charge less than C, negative profit. If they charge more than C, since there is at least one other firm which is charging C, I am not going to get any market. So, I am going to earn 0 profit. So, I am not better off. Similarly, for firms which are charging more than C, if they charge a price different, what different price they can charge? They can charge a price less than C. If they charge a price less than C, they are going to get the market, but again negative profit. So, this is indeed a Nash equilibrium. So, this is a Nash equilibrium, that is true. We also need to argue that no other is a Nash equilibrium. Now, by saying that no other profile, what could be the other profiles? One could be that all the prices are greater than C, but at just one price is equal to C. That is not a Nash equilibrium, because the firm which is charging that C price can do better by charging a price just a little more than C. If it charges a price more than C, then it is going to earn positive profit, and since P is a continuous variable here, we are back to the old assumption of continuous prices. I can always find a price which is C plus epsilon, for example. Epsilon can be any small positive number. I can always find some epsilon and such that my price still remains the lowest price, and in that case I earn some positive profit rather than earning zero profit. So, no profile can be a Nash equilibrium where there is only one price, lowest price, which is equal to C. It is obvious that any profile of prices where the lowest price is less than C is Nash equilibrium. That cannot be a Nash equilibrium, because in that case the price which is less than C, that firm which is charging that price is earning negative profit. So, it can do better by charging a price which is equal to C, either it is in that case it is earning zero profit. What could be the other possibilities? Other possibilities could be that all the prices are such that the lowest of the prices is greater than C. If lowest of the prices is greater than C, and suppose there is just one lowest, the unique lowest, then like the argument that we have given before, that unique firm is going to raise the price and earn better profit. If there is there are two lowest prices and both the lowest prices are greater than C, can that be a Nash equilibrium? Well, the answer is no, because if there is there are two firms or more than two firms which are charging the lowest price, then they are dividing the market, and if they are dividing the market, then one of them is going to undercut its rivals and charge a price just little less than that lowest price and get the entire market. So, basically we have ruled out all the other possibilities of price profiles, and we have seen that none of those profiles is a Nash equilibrium. So, the thing that we are left with, the profile that we are left with is this profile, which is indeed a Nash equilibrium profile. Let us look at some other problems. This is another exercise. Consider a Bertrand duopoly game in which the firm's unit costs are different, equal to C1 and C2, where C1 is less than C2. Denote by PM1 the price that maximizes P minus C1 multiplied by alpha minus P, and assume that C2 is strictly less than PM1, and that the function P minus C1 multiplied by alpha minus P is increasing in P up to PM1. So, if I have to visualize this, what is happening? What we have is that two firms are there, 1 and 2, with costs C1 and C2. C1 is less than C2, which means firm 1 is more efficient than firm 2. It can produce goods at a lesser cost. What we further know is that this alpha minus P minus C1, this is basically the profit function of firm 1. This is maximized at PM1, and we know that C2 is less than this PM1. This is given. We further know that this function is increasing in P up to Pm1, which is true, which you have seen before. Basically, the diagram that is relevant here is this one. We have drawn this diagram earlier also. Now, it will be for only firm 1. If I have to draw this, then this is how the profit function looks like. This is C1, this is alpha. In the middle there is this Pm1 at which the profit is getting maximized. This is nothing but C1 plus alpha divided by 2. What we have been informed is that there is this C2 somewhere in between C1 and Pm1. That is what we know. Notice that if I have to draw firm 2's profit function, then that profit function is going to intersect this horizontal axis and it is going to intersect this horizontal axis once again at the point alpha, because what is pi 2? It is alpha minus P2 minus C2. So, it also has an intersection point at alpha. So, this is the common intersection point, and C2 is somewhere between C1 and Pm1. So, this is the story in terms of the diagram. The question is the following. Suppose that the rule for splitting up the consumers when the prices are equal assigns all consumers to firm 1 when both firms charge the price C2. Show that P1 P2 is C2 C2 is a Nash equilibrium and that no other pair of prices is a Nash equilibrium. So, what is being said is that suppose C2 is C2 C2 are the prices, common price that is charged by the two firms, then all consumers go to firm 1. So, firm 2 does not get any part of the market. Then if this is the rule of splitting the market, if C2 C2 is the price, then we have to show that C2 C2 is a unique Nash equilibrium. This is what we have to show. Now, to clarify the question, notice if the prices are equal, if P1 is equal to P2, but that level of equality is not equal to C2, some other level for example, then the old assumption still holds. The old assumption is that the market is evenly split between the two firms. Only when the prices are equal and that equal price is equal to C2, then the market is not equally split, it goes only to firm 1. That is one clarification. So, we have to show that C2 C2 is a Nash equilibrium and it is the unique Nash equilibrium. Now, C2 C2 at C2 C2, what is the profit of firm 1 for example? Firm 1 is getting the entire market. So, alpha minus C2 is the demand that it is getting multiplied by C2 minus C1. This is the profit and this is positive because C2 is greater than C1, that is given, and alpha is also greater than C2, that is implicit, that we have seen before that the cost is always less than this alpha, the coefficient term of the demand function. So, these both the terms are positive, so pi is positive, pi 1 is positive. Pi 2, what about pi 2? Pi 2 is 0 because it is not, firm 2 is not getting any part of the market. So, all the consumers are going to firm 1, and so this is equal to 0, 0 multiplied by 0, it is 0. So, these are the profit levels at C2, C2. Can someone do better? If firm 1 charges a price less than C2, that if I charge a price a little less, then my profit margin is going down. If my profit margin goes down, then obviously my profit is less than I was earning before. So, by charging a price less, I am not better off. If I charge price a little more, then all the consumers will go to firm 2. So, I was earning some positive profit, now I will earn 0 profit. So, deviation by firm 2 firm 1 is not profitable. Can firm 2 deviate and be better off? If firm 2 deviates and charges a price less than C2, it is going to earn negative profit margin. This part P2 minus C2 will turn to negative, and if P2 is less than C2. If it charges a price more than C2, can that be a Nash equilibrium? Can that be something which is more than 0? The answer is no, because if it charges more than C2, then C2 is the lowest price in the market, so it is not going to get any customers. So, from the point of view of both the firms, deviation is not profitable, and so the firms are going to stay at Nash equilibrium. Question is there any other pair which is which could be a Nash equilibrium? So, other pair, let us call that other pair P1, P2. Now, there will be many cases of this other pair. Suppose P1 is greater than P2, greater than suppose C2. And in that case, is that a Nash equilibrium? The answer is no, because then firm 1 will charge P1 strictly less than P2. So, deviation is profitable. B, suppose firm 1 is charging a higher price, firm 2 is charging a price equal to C2. Then firm 1 will charge P2 and get positive profit. Here firm 1, in this case firm 1 is getting 0 profit. Here also firm 1 is getting 0 profit if it charges a price less than P2. It is going to earn positive profit. Case C, can it happen that P1 is equal to P2 and both are greater than C2? Well, in this case both the firms are getting some positive profit and the market is split, but if in that case any firm, suppose any firm I will undercut its rival, that is charge a price little less than this P1 is equal to P2 and get the entire market. and earn some positive profit, which will be greater than this positive profit. So that is there. What could be the other possibility? Suppose one of the prices is greater than, suppose P1 and P2 are such that both of them are less than C2. This is not a Nash equilibrium, because what is happening is that the market is again getting split, and if the market is getting split, firm 2 is earning negative profit, because P2 minus C2 is negative. So, firm 2 will do better it will deviate than P1. So, there cannot be, in fact, we can show that there cannot be any Nash equilibrium where P2 is less than C2, but can it happen that P2 is equal to C2, but that P2 is greater than P1, and suppose this P1 is greater than C1, because there cannot be any Nash equilibrium where P1 is less than C1. Now, this is also not a Nash equilibrium, because in this case firm 1 will deviate and charge a higher price. So, basically what we have argued is that no other pair can be a Nash equilibrium if the other pair prices are such that both the prices are more than C2, then any firm will have a tendency to undercut its rival. If both the firms are charging price where P2 is equal to C2, and firm 1 is charging a price greater than C2, then firm 1 is going to charge a price equal to C2 and get the entire market and earn positive profit. If the prices are less than C2 but greater than C1, that cannot be a Nash equilibrium, because firm 2 is earning negative profit. If firm 2 is charging a lesser price, it can do better by charging equal to C2. If firm 1 is charging the lesser price, firm 1 can do better by charging equal to, not equal to, charging a price just a little more than what it is charging, but keeping that price less than P2. So, by exhausting all these possibilities, basically we are left with this C2 case, which is a Nash equilibrium. Okay, let us now come to the second part of the question. Show that no Nash equilibrium exists if the rule for splitting up consumers when the prices are equal assigns more consumers to firm 2, some consumers to firm 2 when both the firms charge C2. So, this is part B. So, if C2 is the price pair, go to firm 2. So, we have to show that no Nash equilibrium exists. This is not a very difficult proof. If both the firms charge C2 and if some customers go to firm 2, this notice that this is a case which is different from the case that we had before in A. In A, none of the customers were going to firm 2. Here at least maybe 1 or 2 customers are going to firm 2. In this case, since at least one customer is going to firm 2, then this is not a Nash equilibrium, for the reason that in this case firm 1 can do better by charging a price just a little less than C2, because if it is charging a price just a little less than C2, suppose P1 is equal to C2 minus epsilon. Okay. Now, if firm 1 is charging a price just a little less than C2, then it gets the profit of phi 1, which is a function of C2 minus epsilon. All right. In the case of C2, its profit was this minus, suppose delta represents the loss in profit due to the fact that some customers are going to 2. So, delta is arising because some customers are going to firm 2. This delta was 0 in case A. Now, so if epsilon goes to 0, C2 minus epsilon can become more than minus delta, all right, because as epsilon goes to 0, because as epsilon goes to 0, pi 1 C2 minus approaches C2. So, this part the left hand side becomes higher than the right hand side. Oh sorry, this is epsilon goes to 0, which means that by just undercutting the rival, firm 1 can get the entire market and not share any customer with firm 2, and therefore, this situation of C2 does not remain a Nash equilibrium. And by the demonstration that we have given before, no other pair will be a Nash equilibrium. So, this other pairs are not Nash equilibrium, and this pair also does not remain a Nash equilibrium, which means that Nash equilibrium does not exist in this case. So, that is the end of the lecture. We shall start with some new exercises in the next class. Thank you. In the Bertrand equilibrium of two firms with equal unit cost, what is the Nash equilibrium? So, let the equal unit cost be C, small c, then the Nash equilibrium is unique. It is C. That is, both the firms will charge the same price, which is equal to small c. what is the proof? I will go very quickly over the proof. If the other firm charges C, any firm cannot be better off by charging anything other than C. This is because if you charge more than C, you are not getting any market, so your profit is 0. If you charge less than C, less than the price of the other firm, you are going to get some market, some demand, but in fact the entire demand, but then the profit is negative, which is worse than earning 0 profit, which this firm will earn if it charges C. So, CC is an equilibrium. What is the proof that there is no other equilibrium? This is because if we take any pair other than CC, if the prices are different, if we take any pair other than CC, profitable deviation is possible. Is possible. This is because if the prices are different and both the prices are more than C, then the firm which is charging the higher price will undercut the other firm. So, there is a profitable deviation. If the prices are same, then each firm will undercut the other firm. If the prices are less than C, then either one or both of them are earning negative profits. So, they will deviate and charge more, at least equal to C, which will give them 0 profit. So, this is the demonstration that CC is the only equilibrium. If prices are measured in integral amounts of paise, is there any other Nash equilibrium besides CC? So, prices could be either 1 paise, 2 paise, like that. It cannot be 1.5 paise. In that case, C plus 1 is also a Nash equilibrium, besides of course CC. So, the CC remains an equilibrium, but C plus 1 is also a Nash equilibrium. Why? Because if the other firm is charging C plus 1 and I am charging C plus 1, I am getting some profit. If I reduce my price, I charge C, I will get 0 profit. So, deviation downwards is unprofitable. If I charge more than C plus 1, obviously again the profit is 0. So, C plus 1 is a Nash equilibrium. Thank you.